Stop calling stuff. I think we're recording. We're a little early on that, but it's a little bit of a gloomy day, isn't it? Very bright. It's always sunny in town.
It's Dad's day.
Wrong city for the TV show.
That's why I thought that, bro.
It's always sunny in Tucson.
All right, let's get started. This is our last content lecture before the celebration next week. We're going to do welded connection design. I am not going to post the previous lecture onto YouTube because of the pen issues, but as I understand, the pen got fixed. So hopefully we won't have that again. Cross fingers. But I brought my lovely Expo markers just in case we got to go low tech again. Okay, homework 3.5 is still being graded, but everything up to that should be graded. The solution for 3.5 is up. Now on Monday, both the solution for 4.1 and 4.2 are going to be uploaded and submitted. So that's why for 4.2 I'm not accepting any late homework because you're going to get the solution right after it's posted. But again, Monday we review, Wednesday we celebrate, no class on Friday. So Friday before spring break in steel design you get off. Sound good?
Sorry.
All right. Let's get into it. All right. Okay, so we're in design land, and I'm going to go through this relatively briefly. It would help if I put this in. Because I really want to get into our example for today. I don't think that what we're going to do is relatively complicated, but I just want to make sure that we're clear. The connection that we designed today, we're actually going to have, I think, 4 different designs at the end of the day. And I'll show you what I mean by the design. It's ultimately going to be largely the same amount of weld. It's just going to be different configurations and patterns of weld to meet specific requirements. Okay, so we have our weld metal capacity and our base metal capacity, which I believe after both the previous lecture and the last homework assignment should be relatively straightforward. I mean, it's really not that complicated. What we're going to do now is get into design, and ultimately what we're going to do for design is use our limitations on welds to select a weld size, compute the capacity of a single inch of weld, and then divide to get the number of inches. That's basically it. So our minimum weld size we have to look up. Our maximum weld size we compute. Now remember the reasons for these. The reason for the minimum size weld limit is because of the heat sink effect. The reason for the maximum size weld limit is we want to maintain the geometry of the plate. Okay. Now, so for design, again, the procedure is really simple. Okay, we get our factored load, we choose the weld size based on our limitations. And so what this means again is that we're going to compute our A min and our A max, and we're going to choose the largest weld size that we can up to 5/16. Okay, then we get the capacity of a single inch of weld. So you can think of the inch of weld as like a single bolt. That would be the analogy. So determine the capacity of that connector, that connecting element, and then divide to get how many connecting elements that you need. Now for us in this class, when we lay out the connection, what we're going to do is limit our weld lengths to the nearest inch. Some folks do the nearest inch, some folks do the nearest half inch. I don't really recommend getting more specific beyond that. I don't think you need to be speccing out welds to the 1/4 inch. I mean, you can, but I think that just for simplicity, the nearest inch would be fine. Usually you lay those out in a symmetric fashion, and I say usually because we can lay them out in a balanced arrangement as well. And remember, when we lay out our welded connection, we utilize either longitudinal welds or longitudinal and transverse. No transverse by themselves. Yes, sir?
Is it nearest inch or the inch?
Inch up. Inch up. Yes. So if you compute that you need 10.2 inches, round up to 11. Like that. When we lay them out, again, use longitudinal or longitudinal and transverse. Don't use just transverse because that's a ductility issue. Okay. In design, and this is what we talked about a little bit last time, we want to select the largest weld size possible because the largest weld size typically results in the shortest weld length. And the shorter the weld length, that means it's quicker to deposit, which means it saves on labor, saves on money. Okay? It doesn't really matter from a structural standpoint if you use a large weld that's short or a small weld that's long, because you would, if the area was the same, you'd get the same amount of capacity. But shorter welds, again, not only are they quicker to deposit, but a shorter weld means there's less need for steel for the connecting element as well. So in the end, it's a money saver across the board. Now, common weld size, as we said, is 5/16, and the reason for that is that's about the largest weld that you can deposit in a single pass of the electrode. So now, to be clear, that doesn't mean that you don't use welds that are larger than 5/16. You certainly can. I mean, there are welds out there that are much bigger than that, but that just happens when you have not much geometry and you got a ton of load. Yeah, you need a big weld. So you just kind of have to make do. But again, to be clear, we try and limit that to 5/16 when possible. And again, as I said, never lay out a welded connection with only transverse welds because you get a poor performance in ductility. Now, for arranging the welds, this would be a weld arrangement that's symmetric. So just putting the same amount of weld on either side. So that could be either two longitudinal welds or a longitudinal and a transverse weld. Okay. Now, for a balanced weld arrangement, that's where we lay out the welds in order to eliminate eccentricities from moment. So you'll get a longer weld size on one side of the angle than you would the other. So to be clear, that could be two longitudinal welds, or it could be a longitudinal, transverse, longitudinal. That's fine too. Those are balanced arrangements as well. I'm actually going to show you how to do that one first, because if you can understand how to do that one, then two longitudinal welds is actually a lot easier. So with that, let's get right into it. We have an angle that is a 6x4x3/8, and we are going to design, I have here design balanced welds, because that's ultimately what I want you to do, but I'm going to show you what it would look like if we were doing both balanced and symmetric layouts. But what we're going to do is design that to resist a factored load of 150 kips. I just went ahead and gave you the load because I think by now y'all get load factoring, right? I mean, we don't need to keep beating that into the ground. I think everybody knows how to factor dead loads and live loads at this point. I want to reserve our time for the actual welding component at hand. Now, the angle is an unequal leg angle, so to be clear, for the purposes of our example, this is the 6 inches, right? And just to make sure that we're all on the same page, what we're looking at here is we're looking at an angle that sort of looks like this. And this is the plate that it's going to be connected to. Right? So in this instance, this is the 6 inches. This is the 4 inches. All right, does that make sense? And so the beads of weld that we would be placing would essentially be like right here and right here. Okay. So that's sort of like how we're welding that down. Okay. Now, before we get into the problem, let's just make sure that we're all clear on this. Our material strength from table 2-5 states that we have an Fy of 50 KSI. I believe these were the same values in the previous example that we did, so I'm just going to go ahead and just sort of chug those out. And for the electrode strength, that's going to be FEXX is 70 KSI. And I see that a lot of folks are still like drawing some stuff out, so I'll give you a couple minutes to sort of get caught up. We're in no real hurry today, so I don't want to get too far down the rabbit hole. Everybody good? Okay. Now, our step one is to determine the factored load, but we were given that, so that part's kinda easy. All right. Now, step two is to look at our weld limits. Okay. Now, for a thickness of 3/8. Now, let's go back to that a little bit. For the angle, I know that the thickness is 3/8, but I don't know the thickness of the plate. If I were to know the thickness of the plate, what I would be doing is looking up my min based on the minimum thickness because of that heat sink effect. I'm looking based on that. Now this is in table J24. What is our minimum weld size going to be? So hold on, let me cite that. So remember, we need enough of a weld to avoid the heat sink effect. So what is that for a plate thickness of 3/8?
Maybe 3/16.
3/16. All right, that's a min. A max is going to be what? Is it the thickness or the thickness minus 16? Minus the 16. Okay, I think I can do that one in my head. So between a minimum weld size of 3/16 and a maximum weld size of 5/16, what should we go with? Say it again.
4/16.
Hold on. We choose the largest weld size up to 5/16, which means we choose 5/16 because that's well within our limits, okay? And so to be clear, like if we had A min is, let's say A min was a 1/4 of an inch and A max is 3/8, use 5/16, right? What if it was between 3/16 and a 1/4? What do we use? I'm just curious. If it's between 3/16 and a 1/4, what do we use?
4/16.
A 1/4, right? We use the 1/4, right? That's the one we use. All right. Again, choose the largest weld size we can up to 5/16. So what that means is we can't violate A max, right? So we have to pick between this. We can pick it, we just can't pick past it. All right. Does that make sense? Okay. Now, so now what we're going to do is compute VRN for 1 inch of weld. In other words, our weld length is 1 inch. Okay? So for weld metal, let me scroll down a little bit. What's our expression? It's speed times 0.60 FEXX times 0.707 times the weld size times the length of the weld. So now we're going to take the length of the weld to be 1, or you can sort of just ignore it either way. Just set it equal to 1 so you don't have to consider it. 0.75, 0.6, 70 KSI, 0.707, 5/16. And if you want, you can put a 1 out there, but it won't really matter. So what do we get for all of this? And so I'm going to write some numbers down here. Remember, this is PU. Is 150 kips.
I got 6.96.
6.96, and so what this is saying is 6.96 kips per inch. That's what that's saying. So per inch of weld, we're getting about 7 kips of capacity. Just shy of that. All right. For base metal yielding, we have that. And remember, note that AGB equals ANB. Now, the way that we compute that is just going to be the length of the weld times thickness, right? So if it's the length of the weld times the thickness, and we know that the length is 1, then it's just the thickness. So this is 1, remember? And then 3/8. So what are we getting for that? Because what we're doing is we're determining the capacity based off of 1 inch of weld, so that includes the gross area and the net area as well, right? Because if we're talking about, let's say, here's a plate, right? And we're yanking on it like this, right? So essentially, like the gross or net area, we're talking about sort of like that area right there, right?
I was talking about the P value.
Sorry. So the phi value just for base metal yielding is 1, right? That comes right from, it's in J4. It's page 16.1-137. Yeah. There's only 2 limit states I think we deal with this entire semester that have a phi value of 1. It's this and slip. The slip capacity of a bolt has a phi value of 1. If it helps, once we get back from spring break, phi is 0.9 for the rest of the semester. Because for columns and beams, it's the same. Sound good? All right, so what are we getting for this limit state?
I got 11.25.
11.25, again, kips per inch. Do I have a second? And then finally, base metal yielding. base metal, we just did base metal unit, base metal fracture. Okay, this one's 0.75. 65 KSI, and again 3/8. And so what are we getting for this one?
10.97.
10.97? 10.97. Do I have a second?
Yeah.
Okay. So we have three limit states here, here, and here. Which one are we going to use if we're in design of connection land? What's that?
Minimum.
The minimum, exactly. So this is the one that's going to govern. And so PRN, we're going to take as 6.96 kips per inch. Okay?
I got kind of a dumb question.
What's up?
So if we're doing all this for structural stuff, wouldn't we know that the welds are always gonna be the weakest part of it, or?
Not necessarily, it just depends. It honestly just depends. It depends on the electrode that you're using, it depends on the grade of steel, just depends on the sizes. Honestly. So if you have a really high grade electrode and you're using A36 steel, it's possible that one of these other governs. So, and to be fair, most times it's going to be the weld metal. Most times that's the case.
But if you have basically a higher quality weld than you do the material you're working with.
It's possible. Yeah. I will say though that it's rare. I mean, it is. All right. Well, let's write this down. So I just want to have this. Okay. So let's check some things out. Okay. So I'm going to call this like steps 4 and 5 because we're kind of going to do the same thing at the same time. You'll see what I mean. All right. Let's start off with some symmetric layouts. And I want to be crystal clear, that's not actually what I want you to do in this problem. This problem says I want to do a balanced weld arrangement, but I just want to show you how different it will be between a balanced arrangement and a symmetric layout. So I want to do the symmetric one first. Okay? So in order to do a symmetric layout, let's ask what is the length of weld required. And the way that I'm going to do that is I'm just going to say if I have 150 kips and each inch of weld can supply 6.96 kips, then how many inches of weld do I need for this connection? Let's divide this out.
21.55.
21.55. Do I have a second? Okay. So here are a couple of options for symmetric layouts. Okay, so we have an angle that looks like this, right? That's what we're welding. So what we could do is just weld here and weld here. And I'm just drawing some squiggles here to kind of illustrate where the weld is. The squiggles don't really matter. What really matters is the specification. Here, let me lower this a little bit. Now, what was the size of the weld again that we're using? Okay, so if we're using a 5/16 inch fillet weld and I'm using a symmetric layout, okay, so 21.55, what would I round that up to the nearest inch? 22, and if I did 2 even welds, each weld would be 11 inches long. So what I'm basically specifying is a 5/16 inch fillet weld. That's 11 inches on each side. That is a layout that would work if what we were doing was a symmetric layout. Okay? Another layout could be, so here's symmetric layout number 1. Let's do symmetric layout number 2. Right? Now, if you remember, this dimension is 6 inches, right? Because the angle is what, a 6 by 4 by 3/8? Right? So this dimension is 6 inches. So what I could do is I could place a bead of weld right here, just across the entire back of the angle, or the entire front of the angle, and I could say, hold on. I could do a 6 inch weld right there, but then that's not enough. So I need 22 inches, right? 22 minus 6 is what? 16? 16 divided by 2 is 8. So I could do a 6 inch weld here, and then do an 8 inch weld like this. Here's a layout. Here's a layout. Again, either longitudinal welds or combined longitudinal and transverse. Okay? And again, those longitudinal welds are long enough that I think we can account for that. Like if it was a 6 inch weld and then those 2 transverse welds were going to be only 2 inches long, I probably wouldn't do it because again, I want enough longitudinal weld to actually count on it, okay? But again, here's 2 symmetric layouts. So far, so good?
Now, which one would be like most common?
That's a good question. So for this problem, I'd say this one. The reason why is because remember, you're welding this to a plate, right? That means that the plate only needs to be this big as opposed to that big. So it's less steel. So I would probably go with layout 2 if I was doing a symmetric layout. But I'm not going to do a symmetric layout. I'm going to do a balanced layout. With me so far? Now let's do a balanced layout. Okay? Now balanced layouts are a little different. Okay? So bear with me. So let me show you how a balanced layout works. Okay. I'm going to draw a really big diagram here of the angle. Okay, so here's the angle. Okay, and if I look to the side, what I'm looking at is this dimension here, or this angle like this. here's this. So this dimension 6 inches. This dimension 4 inches. Okay. Let me scooch that over a little bit. All right. Give everybody a sec to get caught up with me. Okay, now, help me out. This is an angle, right? So I'm going to be applying a load of 150 kips. But in a balanced arrangement, I am assuming that that load goes through the centroid, okay? So the centroid is going to be, right about right here. So we'll draw it like this. So probably what I need is this dimension right there. Now remember, keep in mind, this is an L6 by 4 by 3/8. So let me put that right here. It's almost like what we need to do is go to table 1-7 and start looking up centroids for angles. Now, when I say centroid, what dimensions am I talking about? In the manual. What's that?
Y bar and X bar.
X bar and Y bar. That's what I'm talking about. Okay? Now, the question is, which one do I use for this angle? Do I use X bar or do I use Y bar? Which dimension gets me from the bottom of this angle up to the centroid? I'm asking you. Y bar. And what is Y bar for an L6 by 4 by 3/8? 1.93. So those are the loads that I am placing on this connection. Okay? Now, I need to resist those loads with welds. Okay? So I'm going to propose that we place 3 welds on this member. Okay? Now, the weld that is closest to the centroid, I think that weld's going to be longer. I think that's going to be kind of a long weld. This weld up here, I think it's going to be kind of short. And then I might as well go ahead and place a weld along the angle. Now let's think about this from an equilibrium standpoint. I am applying PU and I'm applying that force to the right. And so these welds have to supply resisting forces to the left. Okay? So I propose we're going to get an F1, an F2, and an F3. And so the idea is to solve for these forces required to keep the weld in equilibrium. Okay? Now, just so that we're all on the same page, again, this dimension right here, this dimension is 6 inches. What's this dimension? Where's the middle of the weld? 3 from the bottom. Okay? And just because this is getting a little on the cluttered side, let's move that over here. Is everybody kind of with me on the schematic? Now, okay, let's also be clear, F2, that I can solve for. Okay? F2 is the amount of force I can expect from that transverse weld. But I know what that is, because that is 6.96 kips per inch times a length of 6 inches. What is that?
41.76.
41.76. So what that means is that in order to solve for these forces, you gotta break out some equilibrium. So here's what I'm gonna do. I am going to go back to CE 312, and I'm gonna say, let's sum some moments. Now what I'm gonna do is I'm gonna sum moments about the back of the angle. And by the back of the angle, I mean the bottom. Okay? So I'm going to sum moments about the bottom, set those equal to 0. Okay? So let's see what we've got. So, let's treat this like an equilibrium problem. So if I'm summing moments about this bottom of the angle, do I consider F3? No. F2. F2 is going in this direction, and how far is that from the back of the angle? 3. F1 is going in this direction from the back of the angle. How far is that? 6 inches, right? So over here, I've got F1 times 3 inches, F2 times 6 inches. What's rotating in the opposite direction is PU times a moment arm of Y bar. So, does that make sense? So if I'm summing moments about the back of the angle, PU times Y bar is going this way, F2, oh wait, do I have a typo? Yep, I do. I switched my numbers. This is 6 inches, that's 3. Oh, whoops. So yeah, F1 times 6 inches, F2 times 3 inches. So far so good? So, what don't I know in this expression? What am I solving for?
F1.
F1, right? So, PU times Y bar equals F1 times 6 inches plus F2 times 3 inches. So, F1 equals PU times Y bar minus F2 times 3 inches all over 6 inches. Now some of you are like, wait, we have to remember all that stuff we learned last semester? Yes, seriously. So what is this?
27.37.
27.37 kips. All right, do I have a second?
Yes.
Okay, now, what this tells me is that that upper weld needs to supply 27.37 kips. Now what do I do with that number? Well, that's going to happen next. Okay, so that's going to happen next. But if I wanted to determine how long this weld needs to be, divide by 6.96. So therefore, if we want to call it, I don't know, L1 is going to be F1 over BRN, which is going to be 27.37 kips over 6.96 kips per inch. What does that end up being? 3.93. So we'll say use L1 is 4 inches. Now, Mr. Odell, what were you saying? We sum forces in the x direction because now our remaining unknown is F3. We know PU, we know F1, we know F2, we don't know F3, and we determine that by force equilibrium, just summing forces in the x direction.
Do you really have to do that though? Can't you go by your total weld length?
That's true. Well, okay, that's a good question. So I get what you're saying. I still think it's a good idea to do this from a rounding perspective, okay? Because we want to make sure that that weld is long enough. So what might happen, this might be a downside with balanced welds, but based on rounding, we might end up getting a total of 23 inches at the end of the day. We got to make sure that we supply enough weld on that back leg to resist the force necessary to keep it in equilibrium.
So
Because
if it was 23, you're okay with it?
yeah, oh yeah,
But
absolutely.
it could end up like 21, and then we would have to add.
Which is why I want to go ahead and just do the equilibrium assessment. So, and plus, keep in mind, this is assumed if you're doing a balanced weld arrangement, we never would have done these calculations. We never would have done this. We would have just skipped right to this. I mean, does that make sense?
So you never would have even known your total.
Well, you basically, yeah.
Okay, I see what you mean.
Yeah. I'm just doing it for comparison's sake. I mean, I guess you could do the calc on the side if you wanted, you know, but nobody ever
I'm
really
trying to speed
does.
myself up for the
What's that?
trying to speed myself up for the exam. I don't
There
want
you
to
go.
do unnecessary calculations.
There you go. All right. So now if we sum forces in the x direction, right? Really what we've got is we've got PU this way and F1, F2, F3 this way. And if we're solving for F3, we get that, right? What are we getting for F3? 80.87. What do we get for this? 11.62. So now we use L3 is 12 inches. And so if you want to now lay out that connection, so we've got a 4-inch weld up here, a 6-inch weld here, and a 12-inch weld down here. And honestly, I really don't think you need to draw the little squiggles. I really care about this. Now, does that make sense? Okay. There is another way of laying out a balanced weld, and I'll say note. one way is to just do this. No transverse weld, just 2 longitudinal welds. What do you think is the easiest way to do that? Well, it's to repeat all of the calculations we just did, but with one slight modification. What's that one slight modification? Set F2 to be 0. So you can actually, like if we were doing this problem, you could repeat essentially like this expression, and you could repeat this expression and just set the F2 to be 0, solve for new weld lengths, plug and chug. It'd be pretty easy. So that would be a 4th arrangement, another balanced weld. Does that make sense? So, speaking of, that's exactly what you have on your homework, okay? On your homework, I want you to lay out a balanced welded connection for this problem, but I don't want a transverse weld. I only want longitudinal welds, okay? Now, I did do something to make it a little easier for you, and the angle is an L 4 by 4 by 1/4. Does anybody see what's the easier part about it being an L 4 by 4?
You'll have to do it to one side and then just copy it over.
Well, no. What I'm saying is, so if it's an L 4 by 4, what can you tell me about X bar and Y bar? They're the same. So there's no having to figure out if it's X bar or it's Y bar. It doesn't matter because they're the same, right? So that part makes it a little easier for you. Does that make sense? This is the last topic before the celebration. So, Monday, we have a review for the celebration, so come prepared with questions. That's all I got. I will see you all next week.